So let's do another indeterminate problem here. This one has both different materials and different cross-sectional areas going on in different segments here. So we got these two cylinders. AB, cylinder AB is made of aluminum. It is 1.5 inches in diameter, and it is bonded to a brass rod that is 2 inches in diameter, and it is the aluminum rod's a foot long, brass rod's a foot and a half long, and then both of them are fixed solidly to rigid supports there at A and C. So we got the modulus of rigidity for aluminum is 3.7 times 10 to the 6 psi. Modulus rigidity for brass is 5.6 times 10 to the 6 psi. And we're trying to figure out here what the maximum shearing stress that will occur in each of those cylinders or rods, or whatever the heck you want to call them, is. So, yeah, figuring out what we want. So again, we need some sort of compatibility condition for this. What we're going to have here is, when we twist this thing, oh yeah, I guess I forgot to mention, we also got a torque applied in the middle there. It's applied at the point where they're bonded together, and it is 12.5 kip inches. Yeah. So anyways, the twist that occurs is going to be our compatibility condition, and it needs to be the same at point B. So basically, the amount of twist that occurs over AB needs to be the same amount that occurs from B to C. So just redrawing free body diagrams of these things. So we're going to get a reaction at A, we're going to get a reaction at C, and we're going to, in the middle, we're going to get some sort of torque. I'm going to call that T1 and T2. So those are basically the combination of the those two combined together are going to be the 12.5 kip inches. So basically, when you try to apply the torque, at the joint in the middle, some portion is going to be carried by the aluminum rod, some portion is going to be carried by the brass rod. But we know that our twist can be calculated, and we know that those needs to be the same. So our twist for AB, that's the aluminum portion. That's just going to be the reaction at A times our 12 inches divided by our G divided by our G for the aluminum, and our J. So 1 over 2 times the radius to the fourth, so 0.75 inches. So that gives us our twist can be calculated as MA times 6.53 times 10 to the negative 6 per pound inch. So again, once we plug in a value for MA in pound inches here, those will cancel out and we'll get radians. So that's kind of what we expect. And then for BC, also known as the twist in the brass, that'll be the reaction at C times our length, 18 inches, times the shear modulus, 5.6 times 10 to the 6 psi, and then our J, pi over 2 times 1 inch to the fourth. And here's what we get for MC. The twist in terms of MC, 2.04 times 10 to the negative 6 per pound inch. So again, our compatibility condition is those two twists need to be the same. So MA is equal to MC. So I just solve it. We can solve for MA by dividing MC by our by this term here. Ends up we end up being able to solve MA as being 0.312 times MC. So MA is the smaller of the two, which I guess should not be surprising to anyone. Here, I'll go back to the PDF here. Shouldn't be surprising to anyone because it's it's thinner and it is less stiff. So it is going to be resisting the rotation less. But anyways, yeah, we also have our other portion of the compatibility condition that the total twist applied, the total reactions basically need to be equal to 12.5 kip when we add them together. So adding those together, MC plus 0.312 MC is able to allow us to solve for MC is equal to 12.5 kip inches divided by 1.312. Gives us 9.53 kip inches. And then we got, we're able to solve for MA from that. Just sub 12.5 minus that gives us 2.97 kip inches. So if we want to find out what the stress levels are in those materials, again, just our T times the radius divided by J. So for the brass, 9.53 kip inches times 1 inch divided by pi over 2 times 1 inch to the 4th gives us 6.06 KSI. For aluminum, similar calculation, 2.97 kip inches times 0.75 inches for the radius divided by pi over 2 times 0.75 inches to the 4th. Gives us 4.498 KSI. So again, also shouldn't be surprising that this is, this is higher than this, because this is because they got the same angle of twist, but this is a stiffer material. So a stiffer material with the same strain applied to it is going to cause a higher stress level as well. So anyways, yeah, that is about that.